and there's a lot of them, right? As you can obviously tell. And this is something that's really, I think, one of the most amazing things about how we've come to understand the universe and how it works when it comes to stars, because we don't really have, we don't have like the university here. There isn't like a stellar laboratory, right? Like we can't just go make a star, and study it, right, up close and personal. We have the sun, which is great. I mean, it's close, but it's also incredibly hot, right, and kind of hard to get to as well, depending on how much money you have. But at the same time, we've got a lot of them that we can look at. And so it kind of works like a laboratory. It's kind of like the universe's biggest one, because what we can do is we can look at all those stars individually, collect a whole bunch of data about them, and then start analyzing that data. So, what did we learn last time? Stars are really neat. There's a lot of them. It was a really long presentation. 2. We've collected the following data from mini-stars. Brightness, so how bright is a star, right? And spectral type, and along with that, star color fits in with that as well. Now, spectral classes are easier to, not easier, I shouldn't know, not easier is not the right word, but they are, historically we've been able to collect that data more reliably than color. One of the problems with early photography was that color was kind of shifted toward the blue, so it kind of offset the color data that we were analyzing on stars. But we do have ways of correctly assessing the color of stars. But effectively, spectral type and color line up in terms of the data that we're going to be using today. And, biggest of all, plotting this data reveals interesting things. So, if you were, say, working at Harvard College Observatory, and you were a woman by the name of Annie Buchanan, who had actually a couple predecessors, you have been just drowning in data. Because at this point in history, we've collected a ton of spectral data on hundreds of thousands of stars, right? And we've got a ton of data, right? And we don't really know anything about any of that data. We have the numbers, and we have how it, we have the locations and the numbers and all that. We don't really have anything that's going to tell us about how the universe works, right? So what she did was she started working to organize it and record it. Right? And when you spend a lot of time recording and analyzing this data, you actually start to see patterns and understand how things can be laid out. And she's actually somewhat responsible for the spectral classification we use for stars. If you're here last time, you should remember the accounting book Kiss Me, because that, or Guy, depending on your persuasion. This is like the mnemonic that nobody ever forgets. It's a wonderful thing. And the reason why these letters are so wonky is because we were collecting all this data on hundreds of thousands of stars, and we were saying, okay, this is an O-type spectral type, this is an A-type spectral type, this is a G-type spectral type, and we didn't have any concept of how those would necessarily go together when we were collecting that data. So they were just being funneled into buckets based on some criteria. And then what happened was we ordered them in a specific way, so women at Harvard ordered them in a certain way, and what happened was we ended up going in this order, and we ended up with this unfortunate little old bathroom glue, but we turned it into a cute little line. Annie Buchanan, she classified 500,000 stars. That's a lot. She had an incredible attention to detail and really, I think, delivered a lot of science data into the world that we are incredibly grateful for. Now, independently, a couple of white dudes, Einar Hertzsprung and Henry Norris Russell, talked a bit about them briefly last time. They started thinking, okay, well, now we have all this data, right? We have it classified and it's cataloged, and we know how these spectral types are kind of related, and we have this ordering for them. So, well, how do we want to look at that, right? And what they found was that there is a connection between the brightness of the star, otherwise known as luminosity or absolute magnitude, and the type of light that's being observed, so the spectrum or the color, right? So light goes with brightness, right? And then the type of light that I'm referring to is the spectral band or the color. And yeah, this data was published between 1905 and 1905 and 1913. And what's kind of cool about this though is that they independently came up with this idea. And that's actually why we call them HR diagrams. So this is what happens when you take all this stellar data and plot it. Pretty freaking cool. Should be laughing. No, but this is amazing. I mean, this is the product of just a ton of work using these are things we can't directly study. The only information that we have here is light. That's it. Waves, well, particles sometimes, and we were able to do this because we were able to look at all these stars in the night sky, right? We were able to really put all this together because we had a giant sample size. So, what do we got here? Okay, so this is going to take a little bit. But if you remember the OBA fine girl history, so these are the spectral classes, right? And then we have temperature, which unintuitively goes that way. Okay? So there is a correlation between temperature and spectral class. Okay? So keep that in mind a little bit. And then down at the bottom here, we have this color rating that I talked a little bit about last month. And these are just, you can just think of this as like a number representing the color. And you can actually, on this chart, they've nicely shown, this is kind of the white, this is kind of the red. Okay? Follow so far. And then on this side, we have luminosity and the sun just being a 1. And then absolute magnitude is here. Okay? So, from here, we can actually break it down into, we get all sorts of neat patterns, right? So we have what we call the main sequence, right? Well, this is actually where the vast majority of stars, like our sun, live out their days. We have these weird, off the edge white dwarfs. And then we get into big things like giants, bright giants, supergiants, and that kind of thing. So you can see that there are a lot of interesting relationships between temperature, brightness, spectral class, color, and we can get into mass a little bit as we talk about this. The size of the thing, not the church. So what I'd like to do is maybe I just want to go through the PHR diagrams in a little more detail. This is, I don't know, I walk between which HR diagram representation I like the most, but this is kind of nice and simple, right? So we'll talk about again about the main sequence, which is this line here. We'll get into the giants and the white dwarfs, and we'll talk a little bit about red and brown dwarfs as well. So, the main sequence. These stars are in hydrostatic equilibrium. And what that means is that it's not like they're in some happy restful state, right? Like our sun is in hydrostatic equilibrium, right? And it's still pretty violent, right? But it's what hydrostatic equilibrium means is that the star's gravity is effectively balanced by its outward pressure. Right? So the thing is managing to keep itself in this nice static state properly. Okay? And of course that changes over time. Now, the more mass a star has, the less time it spends on the main sequence. Okay? And also don't think about this, one thing to keep in mind too is, don't think about this as like this isn't like your standard, like a lot of graphs that you see, time is on the bottom here. This isn't like the stars are kind of riding down this fun little, path to sub-dwarfs, right? Like it won't work like that. And I'll explain how that evolutionary process happens in a couple of slides. But yeah, so now the interesting thing about mass is that we actually have a really hard time measuring the mass of stars. It can actually be very, very tricky. And like we can't tell mass directly from the HR diagrams. It doesn't quite work like that. While we have all that data, mass is kind of a missing one. But what's interesting is that we can somewhat infer it. So because we know things about physics and how stars work theoretically, we can kind of say that based on where a star is here, like on this chart, we can actually kind of roughly say how big it likely is. There's a little bit of an estimation that can be made there. And there are better ways to assess the mass of a star, but I won't get into those. Red giants. So now we've got into the giants phase. These are really bright things, roughly a half to 10 solar masses. They last a few million years, and there's a good possibility that we'll get a planetary nebula out of them, which is fantastic for us as astronomers, because planetary nebula are really, really good. Okay. So, how pretty are they, you ask? Really pretty, if you crank the color gain up to 11. So, I mean, these are old pictures. You're never going to see this at the telescope, but it's really great. This is the Kappa Nebula, and then this is the Ring Nebula. The Ring Nebula is really awesome. Like, you can go and look at it through just about, like any decent size telescope, and you will see a nice little ring, depending on how good your eyepiece is and all that too. If your telescope's really good, you can actually see the remnant star sitting in the middle. Right? So, as part of the stellar evolution, so what happened here was this formerly was a red giant. Okay. I don't know how many years ago, some time ago. And this was a red giant at one point. What happened was it effectively spent enough fuel that it got to a certain point where it puffed off its outer layer, right? And this is actually like quite likely, it'll be similar to like what our sun's fate will be. And over time, this expands, right? And what you're left with is this little remnant, right? Which is still bright. I mean, relatively. I mean, it's very hard to see this. I mean, it's one of the like 14th magnitude or something like that, I think. So it's 14th magnitude-ish. So it's incredibly dim. It's very hard to see with a really decent telescope, but it is there. Yeah, and you can kind of, there's all sorts of like really interesting information that you can derive from these as well. And I shouldn't get into this too far. We'll talk about nebula another time, but I just wanted to kind of give you an idea of where that connection comes from. So hey, white dwarfs. So these are they're cool, they're dense, mass similar to the sun, but the volume is considerably smaller. So mass compared to the sun, volume is mass, and then volume compared to the Earth, then, right? So going down, really dense, right? And now we're at this stage where this is the result of a red giant turning into a planetary nebula, right? So you would have something like a red giant that comes over, that's over here, right? And now it's over there, right? So again, keep in mind these are, this isn't like a linear graph. If you want to know what another white dwarf looks like, this little guy over here, that's a white dwarf. So, now we get to the really good ones. Supergiants. These are 10 to 70 solar masses, so really big guys, right? So we're having a few ones over here. And this is, these lines are not, etched in stone in any kind of way. I mean, one of the fun things about astronomy, has been taught by the planet debacle with Pluto and whatnot, is that we're really not great at defining things because we can only define things based on what we know at the time, right? So, we try to like basically I think what happens is once we get too many of one thing, we then have to break it up into multiple things, right? And that's kind of what you're seeing here a little bit. It's just that, as we've kind of delineated these a little bit more, and as we've got a little more data, and seeing that, okay, we can kind of put these in this bucket, and these, and these in this bucket, kind of thing. So, it's a little bit gray, carefully definite. But one of the things about stars that do get this big is that at some point, so right now, stars are they burn hydrogen, and then the hydrogen kind of runs out, and they burn helium, and etc. When we get to neon, that actually breaks down into oxygen and helium, and then the helium, neon fused together with magnesium, oxygen, and then we get, and then the oxygen will fuse and then turn into sulfur and silicon, and so on and so forth. So we get lots of really nice elements out of this, but one of the things that happens is the star just gets a little too heavy. And so, you remember that hydrostatic equilibrium thing that I was talking about? So, our force, pressure of the star is being balanced by the gravitational force. So, it's kind of the opposite of that, what is supposed to happen. So, like, non-hydrostatic unsteadiness, I don't know. It sounds kind of lame. So, like, I don't know, like, yeah, we can call it, like, fire unstable agitation or something. I don't know. Like, effectively what's going to happen here is we're going to get a supernova, right? So what's going to happen is the star is going to become just too heavy for the outward pressure to hold it back, right? And it will collapse in on itself, and it becomes one of the biggest explosions, or one of the biggest energy outputters in the universe. For a short time. So this is not actually a supernova. This is a supernova remnant. So this is the result of a supernova, and this is these are probably a combination of like X-rays and radio waves and that kind of thing, all combined together. You really wouldn't see anything in the optical range. But yeah, and then this is actually remnant 1054, which means that the supernova that occurred here actually happened in the year 1054. And what's kind of cool about that is that we can go back and look at historical records. The Chinese were fantastic for this, but they'll tell you about, they'll have records that actually say, yeah, there was actually a supernova in 1054 in this part of the sky, and you can link it up and tie the supernova remnant that we also found to that supernova. So, yeah. One of the really nice things, and there are lots of other examples of these, but type 1A supernova, again, we like to classify things using letters and numbers, or something like that. The type 1A supernovas can be used as standard candles because they have a known light curve. Right, so when a type 1A supernova happens, based on the physics, we know how bright it should be. And what we're able to do is look at it and say, well, how bright are we seeing it? And then from that, we can actually infer distance. And we'll talk about some other examples like that in a little bit. So, yeah, and we're actually well overdue for one. They should happen about once every 50 years in about a galaxy of our size, and we haven't had one for well over a century, actually. I'm getting old. Alright. So, red and brown dwarfs. So this is when we're getting into this part of the spectrum. These are cool. They're pretty small. They have not a lot of mass. Could even be as small as like a Jupiter. So some people have actually talked about Jupiter as like a failing star. If it had gotten a bit more mass, it could have potentially started up, but didn't. So it's kind of on the hairy edge. So Jupiter's kind of on that hairy edge, right? These were not part of the initial data cataloging that I was talking about earlier. So these actually came along later. So we had to add a couple more letters. So they don't. I have never seen a mnemonic for this, but I like to just say OBA fine girl kiss me a long time. That's easy to remember. talking about these HR diagrams. And I was kind of saying, so there's a lot of interesting things that we can infer from them. And I was talking about these type 1A supernovas and how we can use them as standard handles. It's really hard to tell how far away things are in astronomy. We don't have a giant ruler we can just, stick out there. I mean, we can't fire a signal and wait for the return, right? Our standard methods don't really work. One of them does, the concept of parallax, where if you're orbiting something and you see where it is when it's out over here, and then you wait for you to orbit around, and then you see where it is over here. That gives you a triangle, right? And then you can use some basic high school math to figure out how far away that is, right? So that's a really reliable way of doing it. So this is an example of how we can use HR diagrams with star clusters to tell how far away, how further away a star cluster is. So for instance, we have the Hyades star cluster, and so we know from parallax that I was describing here that it's about 150 light years away. And by doing measurements on brightness again, we can tell that the brightness factor, so these stars, because they're on the main sequence, we know that they're approximately the same type, right? So we know that they should have roughly the same color and roughly the same temperature. So because of this, because of these two parallel lines, if we can just establish what the brightness is, we can then use the fact that the brightness over distances decreases at a square amount. I'm using lots of math, sorry, but because brightness decreases at a square by a square amount over distance, we can then tell how far away that star cluster is. Right? So really all we've done here is taken a known distance, right? Taken the difference in brightness, and then we've basically solved for the other distance. And that's really handy. It allows us to tell how far away things are, which allows us to understand, how far, the space that we exist in and how far away these things are. And that is useful data to amass. So, our sun, which is particularly interesting. It's kind of, it's a boring main sequence star, but it's ours. It gives us light, which is great. It has a spectral type of GQV. It has an absolute magnitude of 4.83. Temperature, depending on which part of the sun you're looking at, but temperature of 5 to 6,000 Kelvin. And it has this color of 0.656. Okay. So where does the sun belong? So I'm just going to point my laser pointer, and you're going to tell me which way it should go. Right? Okay. It's out there. So, it's actually kind of funny because I don't think that the sun was intentionally meant to go right in the center of this, but it's actually like one of the weird ways that, it is a little special, right? So as I was talking about earlier, this isn't like a linear path, right? Like we don't go down the main sequence fun slide for a path along stellar evolution. So, what is the future of our sun? It was born. His parents were very explosive. So anyway, so the star, our sun was formed, yada yada yada. Okay, humans come along, yada yada yada. Humans likely extinct at some point in the future, yada yada yada. Statistics. And then what eventually happens is, so remember I was talking to red giants, right? So what's going to happen here is that the star is going to get, our star is going to get bigger. It's going to engulf Mercury, Venus, and us, or Earth. Hopefully we'll be one gone. I mean, it'd be great if we're still alive. But we wouldn't be here, right? We would have to be somewhere far off because it would just be Earth would just be unlivable at this point. And then, so yeah, at that point, Earth would eventually be engulfed, and we would move on to Mars. And at that point, what will likely happen is, like in and around the Mars area, it'll puff off that outer layer, like I was talking about, and we'll get a big planetary nebula. So other civilizations can look at where we came from and see this really pretty ring. Okay. Nice. And then our star will then turn into a white dwarf. And this is somewhere around, these are in billions of years, so this is around 14 billion years or so. So we're about like halfway through the life of our star. So, how does this look when we go along the HR diagram? I don't really have a name for this curve. It's kind of like an upside down W, maybe an M, the shape an M. So we actually start over here, right? So this is where the sun kind of hops in. So we start with the sun forming from a cloud of gas. That's step 1, right? And then step 2, we get it becomes a orbital star, right? So this is the mass, this is all this gas spinning around and then massing into a star. And then it becomes part of the main sequence. And then, as it gets bigger, it falls into the red giant phase, and then it becomes a planetary nebula, or it gives us a planetary nebula and becomes a white dwarf. So, I wasn't sure how the timing would work out here, so I just wanted to add in a little bit. This is a total shift in focus here, but I want to talk a little bit just about some of the other things that you can look at in the night sky with relation to stars. Binary multiple star systems are actually, like, I really recommend going out and having a look for them. Maybe you should have brought your observer's handbook. There's actually a really great list of binary star systems in your handbook that you can go out and look at. Many of them can be seen with binoculars. Some of them, you may need a telescope for, but they're really neat because when you first start looking at them without any magnification, in a lot of cases, they show as one star, but then we pump up the magnification on it, it actually splits. And what's really nice is that in many cases, these stars are actually different colors. Right? And those different colors, they don't really, when you're just looking, maybe when you're looking at the field, they kind of stick, the difference in color stands out, but when they are right next to each other in an eyepiece, it just pops right out. It's really impressive. This I threw in here just because I just can't do a presentation without having animated image of some sort. These are close in binaries. So I've talked about binary star systems before. When we were talking about these binary star systems, right? What can happen is you can actually get a couple in front of each other, and what happens is when the smaller star passes in front of the bigger star, we get this. We get this dip, right? There you go, the dip. And because we can kind of tell the mass of the stars, we can then kind of like go backwards to use that as a standard example. So won't get into the details of that, but kind of neat. Variable stars are also fantastic. I mean, all stars are somewhat variable, but the really variable stars are ones that the ones where there's a perceivable and noticeable change in their brightness. And some of these can have periods of, some of the ones that I've looked at have periods of, say, like months. So what's actually kind of cool is that there are some that actually pass into the naked eye range. So when you go in the night sky, and you can actually, in a good dark sky, you can see that star, and you come back in a couple months, and you can't see it anymore because it just didn't, right? There are also stars that fluctuate in luminosity over a period of, say, like 3 hours, right? So that's where their peaks and troughs, or their peak to peak light brightness period is. And yeah, they're actually pretty cool to observe too. I mean, if you have a good reference star, right, you can actually look at these and and do some kind of cool stuff. Anyway, I'm running out of time here, but I just wanted to throw those in there as just kind of some things to think about when you're out there delivering. Thank you.
Question?
If you want to talk about anything before you visit next one time, come see me.
What's the maximum distance delay that you can measure in parallax?
Off the top of my head, Jerry?
What's that?
Maximum parallax, do you know what the number is off the top of your head?
How far you can be away and still detect the parallax? Is that
Yeah.
the question?
Yeah.
Are you talking visually from Earth or using the Hipparcos satellite?
I mean, visually from Earth, I think is probably the more interesting case, right? Like it's.
Yeah, again, if you use telescopes that are trying to interpolate results to get past our atmosphere, because our atmosphere is a limiting factor for that. So I don't know what the actual numbers would be on that, but we're quite comfortable parallax measuring from Earth-based observatories to several hundred light years old. But like I said, you have to take into account things like it's wobbling away on you here, so you have to go long observation, average out that position, and then check it 6 months later, go through the same routine.
You know,
Yes. Better to use another Hipparcos satellite.
Yeah, it's not.
They're doing much more refined work.
Good question. Yeah, go for it.
So I looked at the chart, here's the RASC study.
Yeah.
And one of the things that caught my attention is that the mass of the ground water is between, according to that chart, between 1 and 75 Jupiter masses.
Yeah, I mean, I think that was the number that I just slopped in there, but yeah.
So essentially, we are saying that we have a star that is holding nuclear reactions with a mass similar.
Close to, right? I mean, I think you need to be a little bit careful because, again, like what I was talking about earlier is that the range of things and how they occur, I guess, when you get into defining. I don't want you to, like, I don't want to be, like, I'm not saying that, you know, like if we had a Jupiter-sized object, that it would be a star, right? And so it's, like, that's not, I don't know exactly what you're asking, but that's kind of what you're getting at.
The reason I'm asking that is because my understanding was that in order for a star to sustain, to have self-sustaining nuclear reactions, the mass of the star has to be much bigger than Jupiter.
Yeah,
That's why.
it is entirely possible to have that number wrong, right? But they are, like, ground cores are generally fairly small objects. Is probably the bigger thing to take away from that. So, does anyone else want to put rock on something? Takers?
A question.
Yeah, go for it.
Or a comment about groundworks.
Yeah.
Groundworks are, they don't actually have a nuclear reaction for what I've read.
Right.
They're just very hot. So they're just radiating heat out, and so that's why they're on the ground, they're on the bottom end of the spectrum.
Right. Yeah, that's a good point too, because the like where they fit on the HR diagram is really in the very cool, relatively speaking, right?
Yeah. So like also I understand there's another class called the Y class. It's not that official.
Yeah.
And that's getting to the sort of the IR, where that just measures the heat, right?
Right.
Not necessarily the nuclear reaction.
We call white dwarfs, we still call white dwarfs stars, even though they have no nuclear reactions anymore either.
Yeah.
We've got a much broader definition than just being able to be a nuclear furnace.
Again, the possible takeaway, we're not great at much.
Dwarf of dwarfs.
Okay. Thanks, guys.
So they did, yeah, of course.
Okay, so let's start. Good evening, everyone. Welcome to the March meetings of Royal Astronomical Society of Canada, Winnipeg chapter. My name is Chris Keller, and I'll be entertaining you tonight in place of Jay, which is on the travels in somewhere in Indonesia right now, and he was enjoying the solar eclipse a couple of days ago. So, what we're going to go today, this is our schedule for tonight. What we're going to do is have a look at obviously the beginner session just ended. We'll have a few announcements. Tonight also we'll have a little bit of election, which Stan will take care of that. And then we have our regular presentations of constellation of the month and what's up. Unfortunately, Jay is not here, and we're not going to have what's new, but in place of that, we'll have the stand talking about the Nezero this time over there. And then we'll go to the break, and after the break, we'll have the main speaker here, talking on marking the time. And I hope everybody brought the observer's handbook. Okay, so let's go for a little bit of announcements. So, members observing night is always happening on Saturday past meeting. And Brian, is somewhere here? Well, Brian is on there. Okay, so hopefully the weather will hold for tomorrow night, and we can have a little bit of observing. So what time are we going to start, Brian? Around 8 o'clock?
Yeah, we'll start around 8.
Okay. If something, I guess you will send the email, general email, if the weather is not cooperating?
Yeah, that's right.
Okay.
Checking the weather right now.
All right. We also have the Fort White dinner and the show next Saturday in the morning. You want to come down and just talk a little bit about it?
No, I'll just stay with you. That's okay with you.
But talk about it.
Yeah. So, next Saturday, March 19th, is the 8th annual Fort White Dinner Show. I believe it's 8 years. The event has just picked up steam and it's just so popular, so of course we're continuing it. So, the theme next Saturday, March 19th, is planets. And we have a good lineup of speakers happening. And again, like last year, it also falls on the same day as Earth Hour. So I'm going to try and work that in and celebrate that again. It sort of fits with, you know, the environmental sort of educational Fort White does. And I mean, we care too about that kind of stuff. So we're going to start at 6 o'clock at Fort White with cocktails and stuff like that. Dinner, 7 o'clock. Kind of this standard thing. We did the buffet last year. We're going to do that again this year, so it's kind of a little bit of a delay in our agenda, but we're going to roll with it, and it seemed to work out really well. The guests loved it. The price for the event is all handled through Fort White reservations. It's $42 this year plus taxes and gratuities, so it's gone up quite substantially. I don't exactly know the reason for that. Whether Fort White just is capitalizing on the popularity of this, and for them, for sure, yeah, it is a fundraiser. So just to give you an idea, in the 8 years that we've been doing it, the very first year I think it was like $26. So it's climbed substantially, but I mean the meal is fantastic, and of course we're going to have to just deliver, which we always do. Guests are super excited about it. We always get great feedback. There is still tickets available. Again, that's all handled through Fort White, so just give them a call. Normally seats about 80 people or so, that's where we've had the number up to. It's about half full now, so you probably still have some time there. So again, we're going to do the planets as our topic and incorporate a little bit about Earth Hour in there. And if you're not aware of what Earth Hour is, it's a sort of a grassroots movement that is sort of planet-wide. It's bringing awareness to climate change and at a grassroots level. The fundamental message of Earth Hour is that each individual person can do their thing, and we celebrate that by shutting the lights off between 8:30 and 9:30 wherever you are in your time zone. So it's local to you. So lots of information. Play board games by candlelight. We turned off all the lights at Fort White, all the ones we could last year, and did it by candlelight, and it was lovely. I think it worked out really well. So again, it was just by coincidence that it ended up on this day game. So next Saturday, Fort White is the dinner and a show. Call them for tickets if you're interested. Any questions? It usually ends up selling out. Yeah. Maybe they're overcharging. Well, we'll see this year. Yeah, well, I actually just checked with them today, and they are halfway there. So what happens is the last couple of days before the event, Fort White will have to send out a little Twitter feed or whatever their social media tool is at the time that they choose, and it just sells out. So I think if you did decide you wanted to go, you'd have time in the next few days to get in there. But again, call them if you're interested.
Who do we have for speakers?
Returning speakers, everybody, Gail, of course, Jerry, and I have secured Scott Young to be our headliner this year. So, just left. So yeah, that's what we have. And
is there an observing session afterwards?
Yep. You bet. Yeah. Every year other than last year, and I haven't checked the website. It's just a little bit too dodgy, but every year other than last year we've had excellent viewing out there. Last year we did get to view, but not for a huge amount of time, so we'll hope for it again this year. But
All right, thanks, Mark. Okay, now we can talk a little bit about our telescope loan program, which we have for members with maybe new members or members who don't have a telescope. We can take a telescope from us, from the clock, no charge, and usually it's for a month. And if there's nobody else wanting the same telescope, we can probably hold it for a little bit longer. Unfortunately, ID will be needed because if something happened to that telescope, we will be personally responsible for it. And if you want to borrow a telescope, you need to talk to Stan. Stan, where are you? Talk to Stan, and you can have a telescope. We actually have one tonight, so if someone would like to take it, I think this is the 8-inch. Yes. So it's probably available, right? There you go. Okay. We also, as a club, we own the Landing Observatory, and it's all open to all the members. We also have the one inside the observatory, which is very nice to have, especially on the colder nights. To get the key to the observatory and the one, you need to talk to Brian, our observatory director. And in the observatory, we have a 12-inch local telescope, new telescope, and 14-inch. And I guess that's all for that. Boston Pizza tonight, for a continuation of the meeting. One more announcement. Ian brought some books, which will have, raffle. So what we're going to do, we'll have some tickets, and we have some envelopes here, and during the break, we'll just put each envelope to each book, and you just put the ticket to the vote you would like to have, and then we'll go at the end of the meeting for this vote. All right, so you can talk to me during the break for the tickets. And that's for the announcement, unless we have anything from the floor. Good. Okay, Sam, your turn for our election.
Task of taking care of the nasty business, the elections. We held elections last year that replaced many of the positions, so often the terms for many of them are for 2 years. And as a result, tonight's elections are going to be very short because there's only really 2 positions that are open. At the current time, we have as a... These things are always dry. We have Jay Anderson, or should I call him Gordon, as our VP. We have Brenda, who just did the beginner's talk. So they're just going to the point where they're going to be serving the 2nd year of their term. As a secretary, we have Brian, way at the back there. Also wanted to see about the observatory and the Wednesday meetings, the members observing night. As treasurer, we have I put the financial book and we're in very good shape. So we're not going to get into that. So those are the 4 main positions. We also have things like past president, which is Andrea. The importance of past presidents is they often handle the elections and nominations. They're the ones who help bring up people or find people for us to fill in the positions. We also have 2 national representatives that are appointed by the council, and it's Dennis Lyons. Dennis, are you here? No? And Rolando? Yeah. So we have 2 representatives who are sitting on the meetings with their national, and the national has their big discussions about how we're going to run things. They run those. Now, aside from all those positions, we also have 5 council positions. Now, the council positions have sort of changed somewhat. We used to have them that they were 3 years long, but there are some differences from what national tends to have. They're trying to standardize. So a number of years ago, we changed from then on, all positions would be 2 years running. At the current time, we have 3 positions where the people have been in for 1 year and will be serving their 2nd year, and that includes Ralph. Let's see. Kevin Golka, I don't think he's here tonight. Kim G. And Jennifer West. I don't think Jennifer's here. No. So those are the 3 positions that those 3 are filled, and they will come open next year. But we have 2 positions. These are people who have formally served for a 3-year term, and their term is over. They are both able to rerun if they so choose. But the positions that are vacated is one by Chris Keller and one by Sylvia Bracken. So those are the 2 positions that are now open and available. So I'm going to run the elections for the 2 council positions. Can I ask for a couple of volunteers of people who are willing to be scrutineers who are not going to be running for the position as well? Just 2 to help count up the votes. Anybody else? All right. So we have received today 2 nominations for council for the 2 positions. Megan? I'm trying to remember how you spelled your name.
M-E-G-H-A-N.
Oh, okay. And the other person who has been nominated is Ed. No, Ed's not here. Ed's off in Arizona, but unfortunately we had scheduled elections for a time period that he could not be here. So at this time, I'm also going to be taking any nominations for council positions. So, the position of council, actually we've got a guideline of what the position of council actually does, and it's very simplistic. Greet new members at monthly meetings, assist in volunteer events, be a voice of council. Now, probably the key thing about those 3 positions is be a voice of council. Council helps the executive determine the direction of the club. They're expected to not only come in and be a pool of sources for helping getting speakers and different activities, but they're also a driving voice to say, you know what, we should move this way, or we should move that way. We should expand the number of telescopes for lenders, for example, or something of that nature. Or we should have councillors help determine that we needed a star party, and we develop one. So there's a great deal of importance in the positions. So that's the activity, and I'm now opening up the nominations for council for 2016 and the 2017 year. Are there any nominations?
I like the nomination.
Who would you like to nominate?
Nick.
Mick? Mick, are you willing to accept that nomination?
Yes.
Mick? What else is it spelling names? Okay. Are there any other nominations? Oh, good. We get to have an election. So if I could have the 2 people come down and help me. I'm going to ask once more, are there any more nominations? Maybe I'll see if I say it louder, people start. Okay, these 2 gentlemen are going to come around, they're going to help me, they're going to distribute the papers. The papers will be only for the members, so you trust your honesty here. Only if you're a current member are you allowed to vote. So you'll take a piece of paper, pencils will be passed around, there's one for those. I went to IKEA this week. So you can go around and pass it out. I'm going to ask one more time, for the 3rd and final time, are there any more nominations for the position of council? On that note, I formally declare that the nominations are closed. So, everybody will be passed along a piece of paper.
Dad, I don't really know me, so I don't know why she would want to run for the council.
Okay.
So,
Okay. Meanwhile, we'll pass around the papers. That's a great idea. Okay. Megan, if you would like to tell us a little bit about yourself, and especially how you're participating at the current time. That'd be nice.
Pardon me?
Also, how you're participating at the current time.
Oh, yeah.
And we ask the rest of us, we have to be quiet, you can speak, because I'm not going to give her the mic.
Yeah, is there a mic action? That might be easier.
You want some sympathy, go to break out your son.
Hi, everybody. Brendan actually that said, I guess I'm sending the girls to my son down. He's actually the reason.
You remember, right? And you've already got a text.
He's quite a smart little guy, and we wanted a way to encourage his love of space and science and astronomy, and that he knew the planets before he started kindergarten, and we wanted to encourage that, so we joined, and I just wanted to join as the council to give back to you guys, and I also do the newsletter.
Everybody need a pencil.
Anything else about me? So you guys like to know.
Has anyone been missed? Should have a ballot, but doesn't.
Does anybody want to buy some extra?
Thank you.
Well, good evening, folks. I'm sure most of you are familiar with the talks that I've done recently. And I guess one of the reasons I certainly suggested I should possibly run for council, simply because I'm interested, I love teaching, I love explaining things, and I like doing presentations, and I've always had a fabulous interest in astronomy and cosmology. And I guess one of the, I'm not saying, I think the club is wonderfully well run, but I think one of the things I would like to see is perhaps having the beginner's session expanded a little bit more and become more of an educational session, not just focused on people who are just new into astronomy. But, you know, if I suggest this, if I was on council, I would suggest this and see if we can get much more of a broader base of interest, because I'm sure there's, I don't know the telescope, I'm more interested in the theory side, and I'm sure there's other people who are out there too who enjoy that aspect, so we'll see what happens. Thank you.
Okay, so I'm going to ask you at this time to take the piece of paper, right there, share the pencils, take the piece of paper and write down only 2 names. If you write down 3 names, your ballot will be disqualified. So write down 2 names, take your piece of paper, fold it in half, and then where's my scrutineers? We need 1 of the 2 of you to run around, and I want you to put the pencil in here as well as the ballot. No. Thank you. That's a good point. 2 names. Only 2 names. Oh, you're right up here. Did they not give you? Okay. I should tell you at this time that Ed has been, he's not here to represent himself. He's been a long time member of the club, and he participates in all sorts of observing events as well and such. He's the gentleman with the white curly hair. I don't know what his platform is.
The NJ's reign of tyranny. I don't mean that, Jason.
I thought you were doing that. Next year.
Yeah.
So next year, as you can tell, there's going to be like a full slate of openings and candidates. So for those who don't even doing this, there's always a chance next year. Are you getting those pencils back? Here, any going in the bag? Also have glasses and 1 cell phone.
Hey, where'd the wall go?
You don't have a pencil, but I've got something.
outside the room, and there'll be a table here. And count the votes. Any more?
Thank you, Chad.
Anybody have this?
What they call a super delegate?
Anyone else?
Sorry.
Okay, so two gentlemen will just step outside for a moment.
Sure, when was the last time you were like this?
Brian, tomorrow would be the best day for the SA Marathon.
Yeah.
Are you planning on staying the whole night?
Planning on it.
At the observatory?
Yeah, the moon will set, but around 11 o'clock at night tomorrow. Right, so that's possible, yeah.
Yeah.
If we have, it's partly cloudy tomorrow. So that's possible. So you want to do it then?
Myself?
No, myself, or?
I'm just making you aware of that because I'm going to do my presentation in a little while about the SCAs, and that's one of the items about it. The SA Marathon weekend would be this upcoming weekend. It's the closest to the new moon.
All right, let's do it then.
Don't start that. Every time that event occurs, the change in, it infuriates many people, but it pleases me, and I'll tell you why. Because this clock over here will finally be correct.
I think there are about two groups of people in the world that hate daylight savings time the most. One, astronomers. Two, computer programmers. Lots of bugs. Okay? I unfortunately chosen to go with the phone. So if you want a rant on daylight savings time, I can go for hours.
I think we've all decided that the changing back and forth is the real pain. The interesting argument comes in as to which one you want to be on.
Yeah. The astronomer to me says regular time. The computer programmer to me says I don't care. But I think most people would actually prefer the DST.
Yeah. That's what happens.
I think, yeah, if you took a poll.
So what's going to be all your jobs in your place?
Yeah. Or, well, it depends on which way you switch, right? Yeah, I actually had a case where I used to work in a robotics company, and we actually had a robot crash caused by daylight savings time. So, yeah.
We had a guy working for SAP, so he set up by just changing the time a little bit more, was half, so it half.
I mean, there are solutions to it. It's just a Do you know how kids with a leap year? So leap years count for a day, not quite being a day, right? Leap seconds are similar. But just, they happen on a far smaller scale.
Is this on? Yes. Okay, so we have the results. The two winners are Megan and Nick. Okay, thank you, Stan.
All right, so congratulations to Megan and Nick for your elections. That ends my career in the council over the last 30 years or so. And now we're going to have Dale talking about
Yes?
Well, March certainly came in like the lion, didn't it? So in honor of that, tonight we are going to look at the King of Beasts himself. This is one of only a few constellations that actually looks like what it's supposed to represent. Leo is a fairly compact constellation. The lion's head and mane are the group of bright stars that we call the sickle. It's there, but anybody can plainly see that it's really a backwards question mark. The right triangle makes up his backside and his tail. Leo used to have a beautiful long tail, but it was chopped off around 240 BC to invent the constellation Pomerius. Leo is at his highest point in the sky on April 1st, and he's very easy to find. Use the two stars at the end of the bowl of the Big Dipper, but instead of going up the point of Polaris, point down, and then you will come to Regulus, which is Leo's brightest star. Regulus means little king. It's a blue-white star, its magnitude is 1.4, and it's 84 light years away. It shines 160 times brighter than our sun. It's almost exactly on the ecliptic, so once a year on August 23rd, it's eclipsed by the sun, and sometimes it's occulted by the moon. Regulus is a multiple star system. It has an 8th magnitude companion, and the companion has a companion which is 13th magnitude. And there's even a 4th companion, but that one's only optical. It isn't gravitationally a part of the system. It was Copernicus who named Regulus because it was seen as heaven's guardian, one who regulates everything in the heavens. Before that, the star was known as Orionis, the mountain's heart. Leo no longer has a beautiful long tail, so now the end of him is the blue-white star of the nebula. This is an optical double with an orange companion. The name the nebula comes from the Arabic for the lion's tail. When Leo, the constellation, was first named, the stars of the lion were rising and setting with the sun. So we said that the sun was in Leo at the summer solstice. At this point, the sun reaches its maximum power to give light to the earth, and since the lion is the king of beasts, the name Leo the lion was given to this group of stars. I think it's really because it looks so very much like the lion. So the lion has been associated with the sun and royalty since very ancient times. The Chinese summer drought comes to an end in July, so the ancient Chinese saw the curved sickle of stars as the rain dragon who brings rain. In the Pyramid Age of Egypt, a strange mythological creature, half man and half animal, represented the summer sun. Summer was the most important time because of the rising of the Nile, which led to the life-giving floods, which led to the promise of bountiful harvests. At this time of year, lions from the outlying deserts came down into the Nile Valley to seek relief from the heat. Therefore, lions were associated with the beginning of summer. In midsummer, the sun passed from the stars of Leo into Virgo, who represented the harvest. These two groups of stars were in control of the sun during the most crucial time of the year. So, when the two signs of summer met, they gave birth to a creature, the body of a lion and the head of a woman, the Sphinx. In Greek mythology, Leo was the lion that Hercules had to kill as his first labor. This lion was a fierce beast who descended to earth from the moon on a meteor. He ravaged the countryside of Corinth, devouring whoever he met. This lion was one tough cat. His hide was so thick it could not be pierced with spear or arrow or any other weapon. After Hercules had killed his family in an insane rage, he received orders from King Eurystheus to perform 12 labors to purge his sin. The first labor was to kill this monstrous lion. It was so well known that Hercules had no trouble finding its cave. As he approached, the lion showed himself, and Hercules shot an arrow right to its heart. The arrow bounced off and fell to the ground. He tried to kill it with his sword, but the sword bent in two. He beat the lion with his wooden club, but the club was smashed to pieces. Hercules battled the lion for a full month. Eventually, he was able to grab the animal and strangle it to death. When he returned to King Eurystheus with the lion, the king thought it was still alive, and he ran away in terror at sight of it. He screamed to Hercules to take it away, take it away. So Hercules took it away. He left the city, and he used the lion's own claws to cut off its tough hide, which he wore as a cloak. And the lion's head became his helmet. Pictures of Hercules nearly always show him wearing this armor. To commemorate this battle, the spirit of the lion was placed in the sky, where it is no longer deadly, it has become beautiful. Leo is far enough from the Milky Way to let us look into intergalactic space. Here you can observe any kind of deep sky object you want, as long as it's a galaxy. The distance to the galaxies in Leo is 30 to 40 million light years. In general, these galaxies are not big and flashy, but there sure are a lot of them. Besides being really dark adapted, the best technique for observing galaxies is to use a bird of vision. By looking slightly away from your target and keeping your attention to it, you will more easily pick up details like modeling and spiral arms. Leo has 5 Messier objects: M65, M66, M95, M96, and M15. M65 and M66 are a great pair of galaxies that are in the same field, along with NGC 3628. M65 was discovered in 1780 by Charles Messier's friend Pierre Méchain. It's seen nearly edge-on, and it measures 10 by 3 arc minutes, and its magnitude is 9.3. It's very close to its neighbor in galaxies, and it's under their gravitational influence, but it looks very much like a typical spiral galaxy. It has a bright center with a stellar nucleus, tightly wound spiral arms, and a prominent dust lane. Near the lane we can see some knots, which is where new stars are being formed. M65 is roughly 35 million light years away. M66 is a little bit larger than M65. It's 9.4 arc minutes, and its magnitude is 9. It was discovered by Pierre Méchain in 1780. At the same time, he discovered M65, obviously, and it's also about 35 million light years away. It has a central bulge, and its spiral arms are deformed, possibly because of gravitational interaction with its neighbors. Its arms seem to have been pulled above the main disk of the galaxy, and if you use a vertical, you will see some modeling. About a degree north is the other member of the Leo trio, NGC 3628. This one was discovered by William Herschel in 1784. It's the faintest of the trio at magnitude 9.5, but it's a little bit bigger. It's 13 by 3 arc minutes. It appears fainter because we see it edge on. If you use low power, you will see all 3 of these galaxies at once. This is a real picture. I did not cut and piece this together. Another trio of galaxies in Leo is M95, M96, and M105, although they're a little bit farther apart. M95 is a typical barred spiral with nearly circular arms. It was discovered by Pierre Méchain in 1781. This galaxy is about 38 million light years away. It's roundish, it's 7.3 by 4.4 arc minutes, and it has a bright core. Its magnitude is 9.7. M96 is one of the brightest of this group of galaxies. Like M65 and M66, these Messier objects weren't exactly discovered by Charles Messier, but by the French astronomer Pierre Méchain. Méchain was mostly responsible for finishing Messier's work. M96 is about 38 million light years away. Including its spiral arms, it measures more than 100,000 light years in diameter. It's oval, it's 7.8 by 5.2 arc minutes with a bright core. The core is non-stellar, it's about 1 arc minute in diameter. This is a tight spiral, and at magnitude 9.3, it's brighter than M95. These two galaxies are in the same field of view, they're just 42 arc minutes apart. About 1 degree to the north of these two, and in the same low-power field, is M105. This one is magnitude 9.3, and it's also 38 million light years away, and it was also discovered by Pierre Chan in 1781. M105 is an elliptical galaxy. It measures 5.3 by 4.8 arc minutes, and it has a bright central core. Every picture of it also includes NGC 3384 and 3389, which is a more distant background galaxy. Another really nice galaxy in Leo is NGC 2903, which somehow escaped Charles Messier's telescope. I really like this one. It's bigger than any of the Messier objects. It's 12 by 5.6 arc minutes, and its magnitude is 8.9, which makes it brighter than any of the Messier objects. It's just 1.5 degrees south of the lion's nose, which makes it extremely easy to find, which is one reason I like it so much. This is a barred spiral with a really nice symmetry. It has a 1 arc minute core and 2 faint arms. It gradually brightens towards the middle, and this core is slightly off-center just towards the east. There are many, many more galaxies in Leo than just these. Most of them are between the Nebula and Regulus, with a few more scattered around Gamma. Most of them are quite small, so the bigger the telescope, the better. I'm sure we're all aware of the Leonids meteor shower on November 17th. But did you know that Leo has all these other meteor showers? Just to the north of Leo is the constellation Leo Minor, the Little Lion. Little is right because this constellation is very small and very faint. Its brightest star doesn't even have a proper name, and the only really, really dark skies you even glimpse it. But that's okay because the more felines there are up there, the happier I am. I knew there was a reason I like this one.
Start with this picture. This is the very thin crescent moon. Those who people who are in the RASC probably already saw this as I sent this out this week. Bill had sent out a nice message explaining that you can see very, very thin crescent moons, more specifically in springtime, because that's where they're highest in the sky for us. And just the whole geometry of the situation works out very well. It's kind of neat because it's so young. This was about 22 and a half hours old, and you don't even get a half a crescent out of it. Basically, it's when you see moons like this that it tells you that the moon won't interfere with the sky, it won't be a pollution source, and so you won't have to worry about it for the Messiers. So tonight's presentation, basically, I'm going to give a little bit of a review of the upcoming Messier Marathon opportunity, or preview of it, talk about some of the challenges, how to handle some of those challenges, and then talk about a few of the objects to start. Now, for this year, because the Messier is the most favorable, when we're in our latitude, it's most favorable somewhere around in mid-March. So this year is actually a very good time period to do it. From our latitude, the maximum number of objects you can see is only 109 out of the 110. One you cannot see. If you're further south, you could gain the 110th object, but it would be near the end of March if you'd want to be looking for it. So basically, most people try to do this on weekends because a lot of people actually work for a living, and so they do their observations on the weekend. This year, the primary weekend, the primary day that you probably want to try this would be tomorrow. If you fail to do that, you could also try again in about a month's time, right after the April new moon, and that would be the weekend of April the 5th. The one difference is when you do April the 5th is that the two objects that you see first in the March time frame will have set or gotten too low and you won't be able to see them. But you will gain M30, which is one object that you can see from us here in March. So here's the key to seeing it all. You definitely need dark skies. You should know how to use your scope. You should have some idea of the sky, some familiarity, particularly since the fact that you've got to do some of the searching early in the morning and late in the evening, just when the skies aren't totally dark and things aren't totally visible. And one of the problems is that the first two objects are two of the hardest ones to see. And the other thing, of course, you need is good weather. So usually people try to have a couple of days to do this. So you need clear skies. You need to have a clear east and a clear west, specifically because you want to see some objects that are just rising or just setting. And so I would suggest Glenley is actually a good spot, or you'd want to be somewhere darker, but again, you would want to be able to see down to the horizon. I like to promote Glenley as a spot to do this because it's got some of the other comforts that come in handy. A warm room, a restroom, and a means to have a warm beverage. So when you get a little bit of a chill in the middle of the night, you can go make yourself a nice tea. So the key here is you want to be able to see down to the horizon. You need to know how to use your telescope. So you want to set your telescope up early, have it ready to go, and you want to have it calibrated with the finder scope. That means you want to make sure that when your eyepiece is in that scope and you're looking at something, that your finder scope, the crosshair, is exactly aimed at the same spot. That's really important. You want to be able to have those two systems well aligned. You also need to know field of view in your finder scope. Jerry talked about field of view a few months ago when he was talking about, that's the area that you see. When you're looking there, you're generally seeing about a 6-degree field of view, apparent field of view, with an 8x50 finder scope. Now, for me, the preference is to have a powered scope, but you could also do this whole thing without a power scope with a zero power finder. It will work, and I'll show you how. The other thing you want to do is you want to have a nice low power, wide field eyepiece. You don't want anything with the narrow field. The wider the field, the more chance that once you align it, that the object you're looking for is going to be in that field of view. And then you want to have something like a Barlow, because some of those objects are pretty small, so you're going to want to have higher power. And in particular, some of the galaxies, they always talk about some of the ones in Leo, and they're pretty big, but there's a lot of others that are much smaller. If you want to see any detail in them at all, you want to have power. The thing that you should know ahead of time is that with that eyepiece, you should also know what the actual field of view is. So you kind of know when you're shifting around, when you shift over one full field of view, you know how much of the sky that you've moved over. So part of the skill, or part of learning in your way up, is learning the skill of how to move your scope around. So here's a prime example. When you're looking through a Dobsonian scope, that when the object's moving out of view, you're learning which way you pull the scope to put the object back in view. That's part of the learning process of how to learn with the telescope. Someone was mentioning to me that they were having some challenges, so I'm going to just talk a little bit about this as we go on. But this is a key thing, to learn how much you move it and in which direction you move it into. You've got to know about the finder scope, because depending upon whether it's a straight through or it's got a diagonal, the view that you will see will be shifted around. And here's a prime example. Well, if you're looking through a straight through, it's not too bad. It's the normal effect that you have when you look through a refractor that flips it upside down. But if you do a diagonal, then you've got another mirror, and all of a sudden it flips it backwards. This is kind of key, because when you're looking for it and you're trying to find it amongst certain stars, you've got to think in your mind, how are those stars being portrayed in my finder scope? Are they being flipped this way? So that you know that if there's two stars and you have to go in a particular direction away from them, you've got to know that with a refractor that you've got to go in the opposite direction because the view is flipped. So this is one of the key essentials that you have to learn ahead of time prior to doing the essay, so that you understand which way you're going. One of the other challenges about learning which way is up is the fact it depends upon what type of mount you have. If you have a Dobsonian mount, like this Osmond mount, well, you move left to right, up and down. That's fine when you're going south and you're moving this way and that way, it works pretty well. But when you go to the east or the west, all of a sudden you're not truly moving up and down, left or right, you're not moving degrees higher in latitude and longitude, you're actually shifting at a diagonal all the time. So that's one of the reasons why ahead of the essay you practice with your scope and you learn which way the objects are going to be. And it's going to be different in the east, different than the west. This applies more to when you're using a star chart and you try to figure out, okay, I see these two stars, which way should I shift my scope in order to find the object that I'm looking for? With an equatorial, you're always following along the lines of longitude and latitude, or you're shifting along those. And that helps if you know sort of where you are, or if you're using this thing called setting circles on it. And we'll talk about that too much. But the fact that you can move, up towards the north or further to the south, and that's the way when you see star charts, that's the way they're set up, right? They've got the lines and this, and you look and you see on the star chart that here's two stars. Well, you say, oh, the object we're looking for is to the north of it. So an equatorial scope makes it easier to do that. The key is you've got to learn how to use your scope. Now I'm going to talk about one interesting thing here. This is called the geometric way. People have talked about star hopping, and star hopping is a method of finding an object by going from a certain point and following along a list of stars that you can follow in a star chart. Well, geometric method is different in the fact that it starts talking about shifting relative to certain stars. We form a pattern. And apparently, this is easier for our minds, our complicated brains, find this an easy way to move things. So here's a prime example. When you're trying to go and you're trying to find M106, well, you learn that you go the distance through here, continue along the line, approximately the same distance, not quite the same distance from there, and you form kind of this little triangle, and this is the area that you'll be locating. Another example is you define M51, where you start to realize that you will be this little triangle. So when you're looking through your Tellerad, this is the circle, the outer circle of the Tellerad. When you're looking at it, you're setting it up in approximately this place, so that this star is not in the Tellerad, this star is not in the Tellerad, but it's just down to this location relative to that little triangle. This is called the geometric method. I mean, this generally is valuable for finding it when your object is not near a bright star. Now, 19 of the Messier objects really do not have a bright star near them. So the majority of them are easier to find. Here's a prime example of easier ones to find. If you have if you put your finding scope and put it on the star here, Chad? HAB? Jerry? Yeah. David, is that fat? The name? Right. Oh, that's gravel. Pardon me, there's that. Right, pardon me. Okay. So you know that if you put, there's your Tellerad focus, there's the circle that you're looking through, and then if you put it up there, that these two objects are in the vicinity of it, and that helps you align it. So this is another method, and maybe as Vic says, at one session, we can, one of our beginner sessions, we can go to this, go further and help people learn about it. The other challenge is to need to learn to know the sky. You basically have to know it so you know whereabouts the objects are going to be. This is the little planisphere that we hand out to the public, and this is just a prime example. You need to know what's going to be up and when. There it is, set up for about 7:30 time frame, just when it's starting to get dark, and that's showing you the sky. I move one more slide, I can do it a little bit closer, and this is actually pointing toward the first two objects that you look at. So you can see here's the western horizon, and you're looking for two objects that are not far off the sky. And if you shift this for half an hour, those objects are so low in the atmosphere, you won't be able to find them. So we need to have a few tactics of how we're going to approach this. And here's a list of tactics, and I'm going to go through these just a little bit. The first ones are, you need to have a list of order of the objects, because they're not all lined up from 1 to 110 for the Messier aircraft. They're found indiscriminately around the sky, so you kind of need to know which ones you want to do and when. And then you need to have suitable charts to tell you how to find them. I'm going to tell you probably one of the easiest ways to do it. Buy this book. This book is great because it's made for year-round so that you can do the Messier Marathon any time of the year. You won't do all 110, but any time of the year you can do it, and it has all the things, including having an order list, binder charts, and details, and I'll show you a little bit more about this. There's one of the pages in it for the first objects that we're going to be looking for. M74, it's telling you here's the first object to look. There's the Telluride circle. So I was talking about if you have the zero power binder, that's, you're looking through it, it's showing you the little red circle. That's where you're showing the little red circle lined up just off that star, and with the offset at that degree, you should have the object inside the field of view. So the other thing this chart does tell you is down here, it says by the way check off there. So from the time you start, you should be able to find it within 5 minutes. The other thing this has is it'll have a lot of details, and I like this. So if you do have a finder scope, this shows you what the brightest stars in the finder scope should be. And it tells you if you've got a right angle or a straight tooth. So it kind of gives you an indication. When you look in there and you say, hey, well, I can see these stars, you go, but I don't see the object, oh, I've got to shift it up to that location there. That's the value of the finder scope. We'll show you the famous stars. Plus this book has a nice little diagram of basically a sketch of what it looks like. And this is if you had a 3/4 degree field of view, that's about how big the object should be. So when you look at that diagram, you should be able to say, okay, there it is, there's the object, and I should be able to see this little chain of stars that is in the field of view. That's how I know I've got the right object. So you want to practice the very difficult areas ahead of time as well. That doesn't help when I tell you that tonight. But maybe if you do this in April, the key about the difficult areas is that when you get to some areas, such as Virgo, is you start to say, well, there's a whole bunch of messy objects. Now, wouldn't that be easy if that's all you have to do? You just go for one and you hop to the next, and you kind of hop to the next and to the next, and you can find them all. That makes it really easy. There's only one problem. It's not the only objects that are there. There's a whole bunch of MGC, a whole bunch of other galaxies that are there. So if you're going to know what you're looking for, you've got to figure out where these objects are against everything else. Well, okay, there's M60, but hey, there's a whole bunch of other objects there. And as you go towards M59, you're going to notice that, then M58, your field of view, you'll keep noticing that there's other galaxies in here. You go here, well, which one is it? So this area is an area that you pretty well have to go through ahead of time in order to be able to identify which ones are actually the Messiers. Generally, the Messiers will be the brighter ones. Now, the other thing that I would suggest you get is this chart. This is the Messier object chart, and this is all to scale. So this is all at exact the same power. So this will kind of give you an indication of whether the object you're looking at is actually what you're looking for. Here's M42. Well, the right angle is so big, so only showing the part of it. Here's M43. Just huge objects that are so big that they're out of scale. But it also shows you that there are small objects. There's a ring nebula, and there's some smaller galaxies there. So it shows you that sometimes the galaxies are going to be big and large and rare, and in some cases they're going to be much smaller and fainter. And then you find this one, you're going to go, oh, okay, that's what it is. I'm looking for something too big. So this is a good chart to have. It kind of gives you something to look at, to compare, to see if it looks anything like what you're doing. So some of the other tactics that you really have to do is you have to start early. You really begin in twilight. This starts before the sky is dark enough that you go, oh, now it's time to observe. And Bill was pointing this out when he told me about wrote a little article to our little RASC list about looking for the moon. You're almost doing the same thing. You're looking about half an hour after the sun has set, the sky is just starting to get into the early twilight. That's when you're going to start looking for some of the stars and try to find some of these brighter stars in order to determine where you're going to find that galaxy. So you start early, you begin right at twilight, because here is the first two objects that you're going to want to find. This one is going to be the first one to set, so it's going to be the first one that you're going to be looking for. And normally, during the other times of years, when you're looking here towards Pisces and Cetus, you're looking at these objects are actually this way, right? They're higher. They're like this. But now they've turned and they're coming near where they're setting, and they seem to be on their side. So here's the other catch that you have to, the other difficulty that you have, is that it's not in the way that you normally see it when you're looking at it when it's highest in the sky, when it's at its brightest. So the earlier objects are some of the more difficult ones to find. This one is also near a bright star, so when you put your microscopes in this area, you should be able to find these easy enough. I mean, it's not that they're very faint galaxies, they're just in that twilight zone. Plus, they're low on the horizon, which means you're looking through more atmosphere, and now the sky is kind of blocking the light from it. You lose a few magnitudes of brightness looking through the atmosphere. So you got to begin and go for a couple objects that are really hard to find. A couple other tips is you basically move from west to east, from where they've set, and then you just keep going along and doing more objects, west to east, picking off from the south, which are going to be the first ones to set, towards the north. And keep in mind, some of the objects that you're going to be looking at actually are solar, will be there for the whole night. That's more prevalent for us here. When you go down south, it's not the same. Objects you're looking for in Big Dipper are gone. Now, okay, the easiest objects first, get the easy ones down, then you can afford to spend the time. You don't want to spend the time looking for something that's difficult, not find it, and have this done on an easy one. And then locate the objects and constellations that you know better. They're the ones with the brighter constellations. So, the key is, get started early, get these two. If you can get these two objects, trust me, once you've got them down, you're going to feel confident, hey, I can do this, and then you can move along and start seeing the objects. This is, in fact, the two first objects, and they're very decent little galaxies. They both have very nice bright inner cores, so you should be able to detect them, but you will be looking at these in twilight. So you won't be able to see, the arms of this. You'll be seeing just the fact that there's a brighter core here. You won't see all this detail. They'll be washed out by the sky. So the key is, while you're out there and you're doing these objects, enjoy. See how many you can get. Yeah.
Well, 33 and 77. So you don't go tomorrow night, you go the next night, you're going to miss it. How long can you see 33 and 37, and when would it be?
73, 7.
Those are the two that you're going to miss if you miss tomorrow night.
You know what? That's why they plan for certain weekends around the new moon, because then the moon's going to be interfering with the moon.
But there's not like Monday.
Well, no, it's not a matter of days, but probably within about a week and a half, you'll get the point where you...
Well, you can come out and see those two.
Yeah, like I say, by the time you hit the April time frame, 4 weeks later, with the next new moon, you're not visible at all.
Okay.
At all, you won't be able to find out. So it's probably a matter of a week and a half you have after that you might be able to see them. This is actually, March 12th is actually a nice day for us because it counts much.
Okay, because it's early, but where's 33?
33,
like is it in the morning, then at 3 o'clock, or do you have to wait?
33 is in the evening.
Oh yeah, so they're both 33 and 77 are close together.
Yeah,
at the same time.
So M31 is the easy one, right?
Yeah.
Andromeda Galaxy, that's the easy one to find.
Right.
That's great. But 33, you're right. It's one of the galaxies that's actually low surface brightness. It's hard enough to see. So what do? You go for M31, you catch that one, right?
Yeah.
You can do 110, 31, 32, 110, grab those three, you grab them quickly, you check them off on your list, I've got those three, and then by the time you slide down, then you start looking for M33, which is going to be a challenge, because it's going to be in that sky. That's why you want to do the objects, and you do them quick, especially at the beginning. Bang, 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 bang. You see it, you confirm you've got it, you go. Great.
Right, I'll be brief. We have a long meeting today, so this is what's up for March and April. Okay, so for the planets, basically Jupiter's going to be up all night, so we can see that tomorrow. Saturn and Mars will be more towards the morning. They'll start to rise, I think, around after 1 p.m.
After midnight, okay, so Mars, starting March the 13th. Okay, so I like to show this, gives you a brief or a quick example of where the planets are in relation to Earth. As I mentioned, Jupiter's going to be pretty much all evening, and then Mars and Saturn's going to start to rise around after 12 midnight tomorrow. Next, here I'll show you again, we have, this is around 10:45, moon set till 10:54, so the reason we verify tomorrow, this shouldn't be a problem tomorrow. And I'd like to show this because unfortunately Saturn and Mars is pretty low in the sky. So, and I had this set at 5 a.m. in the morning. Now for the calendar, here we have the new moon on March the 9th. Of course, this weekend we have the daylight savings time, so we move our clock 1 hour ahead. The equinox is going to start March the 20th. And then we have actually a lunar eclipse on March the 23rd. I think it starts around, 5:47 a.m. And then we have the sky full lights starting at March 25th and be on for the next 2 weeks. And I don't know, when I see it in Arizona, I don't know, but I guess I'll find out when I get there.
Yes, you did.
Right?
You did, for current pictures of it.
Okay, oh, you are?
You did.
You did? Okay, all right. All right, and of course we have the comet Pentagon is still visible. All right, so about the lunar eclipse that starts March the 23rd. So basically what is, because the transition from here to here, it's only going to be for about 2/3 of it. But unfortunately, because it's going to be quite dim, the moon apparently is going to be a lot smaller. It's going to be smaller. The apogee doesn't happen until March the 25th, or March the 25th, but the transition from this to this, it's going to be very gradual, and you're not going to see it until it comes up to here, right about there. So it's going to be such a gradual, you're not going to really notice until it gets there. That's the inaugural lunar eclipse for March the 23rd. Now, of course, we are in the visible part of it. This is where we're going to be able to see it. As far as Asia, we're going to be able to see it. And what is that? The time I have here? Yeah, so this is where it's going to happen at 11:48 Universal Time. So that's what's going to happen. I think that's around just before 6 o'clock. 6:48. 6:48? Yeah, I know. Okay, now I'm just going to explain a little bit more of the symmetrical lights. Okay, basically it's just a soft pyramid of white light. I like to show this for the new members because they're not really familiar with it. Of course, the geometry is going to be right. Now, it's only going to happen for the month of, I'd say February and March. The next time it's going to show up is going to be in the fall, starting in September, October, I believe. Be the next time that we'll be able to see it. But this is in the evening. So maybe tomorrow, no, not tomorrow, but not until March 25th. That's in the evening part of it, after half hour of the twilight. It's going to happen. Okay, a little bit more history. Of course, it's moonlight, light pollution. It's going to affect the zodiacal lights. So make sure we have a good clear night. Now, okay. So again, it follows the electrical path of the sun here. This is where the sun is going to trace it. So roughly right about there, we should be able to see a pyramid of white light. Now, I just show you some brief examples of how it could look like. So we see a little bit of pyramid of white light there. Then we see another one here. We see a little bit of pyramid of white light. And there's no one there. Now, I came across some comets in March. So here's a list of comets that should be visible. We have Catalina, that's visible from binoculars and small telescope, Pan-Star. These two are going to be visible for a small telescope. Now, for this one and this one, of course, obviously you need to see it, unfortunately. But I think this one right here, this Pan-Star right here, is going to be, I think it's going to approach Earth around, this month, June. And it's going to be a distance of 0.06 AUs starting in June of this year. Okay, now this is the magnitude of Catalina. So we're in March, so we can see roughly by the end of March it's going to be pretty dim. The magnitude of, projected magnitude is going to be around 11. And And of course, you know, by September, October, it was way too general, so you do have a 16-inch telescope to go look at it. This is roughly where it's going to be. Okay, so right about there, and right about here should be the double star cluster, and that's where the comet would be. And this is a picture from Sheila. It was back in January. Now this is the projected path of the comet. So roughly it's going to be here on February the 17th, February 2017. And that's about it. So, and that's it. Right. Going to be brief.
Thank you, Brian. Okay, so we're going to have a rather short break. And don't forget about the books, so we can just look at them, and then we'll take that some and then we'll draw after the main speaker. All right, so let's take a break.